MBGS, and
This meeting is being recorded.
This meeting is being recorded, so it will be available for others later. Just want to say, please mute yourself and turn off your video so we can narrow our bandwidth here and take up less space. We talked a little bit at our committee meeting about having a field trip next fall to Hocking Hills in Ohio. So be aware that that's a possibility coming up. Closer to now, we have the GSA meeting in Grand Rapids in May, and there are associated field trips with that as well. So keep those in mind, especially Friends of the Pleistocene. And if you look in our newsletter, there's some information about that. So I'd like to introduce our speaker tonight is Chanse Ford. He's a physical scientist with the USGS Upper Midwest Water Science Center in Lansing, where he applies numerical modeling techniques to stimulate regional groundwater fluxes. And Chanse got his Ph.D. at MSU, his master's at Western, and his bachelor's at University of Southern Indiana. So thank you, Chanse, and welcome.
Yeah, thank you. Thanks for having me. All right, I'll go ahead and share my screen here. All right. So yeah, thanks for having me tonight. I'm, as Jennifer said, I'm Chanse. I'm a physical scientist with the Upper Midwest Water Science Center for USGS here in Lansing. And the what I'm presenting tonight is actually my PhD dissertation defense that I gave this past May as I was wrapping up my PhD in the Department of Earth and Environmental Sciences at Michigan State. So my dissertation was focused on snowmelt hydrology and the changes to that from warming winter temperatures in Michigan and the eastern United States. Okay. So I had several motivations for researching this for my PhD. You know, snow is a critical component of Great Lakes hydrology. Some areas of the Great Lakes receive some of the highest snowfall totals annually in the continental US. And so it's a pretty significant component of the overall hydrologic budget of the region. And the scientific literature into snow hydrology and the changes resulting from warmer winter temperatures driven by global climate change is fairly lacking in non-alpine settings. Most of the literature focuses on, you know, mountainous regions like the Rockies or the Alps. And so in the studies that do focus on non-alpine and non-Arctic settings, the scales tend to not be ideal for what I was interested in. Either they're too large, looking at, you know, very large regional or continental scale settings that's too coarse for any sort of local or regional interpretations, or they're too small scale and focused on very local studies, very small areas, and so that limits their applicability to a wider areas that we see across the Great Lakes. And there was some anecdotal drive to this as well. I've lived in Michigan since I started my master's degree in 2014. And while living here, I noticed that a lot of the winters, we didn't have this traditional snowpack that would start, you know, in December and build up throughout the season and persist for several months and then melt in one big event in the spring. But rather, we would have what we see here in these pictures. This is just from my backyard in Pinckney. And so the figure on the left is January 18th, and you can see there's 3 or 4, maybe, you know, 6 inches of snow in some spots out in my backyard. And then just a few weeks later on February 1st on the right, you can see most of that snow is gone, everything except for what I'd shoveled around the patio. You can see the grass poking out, and we're getting new snow on top of that. And so this is very typical of what we've seen in recent years. And as we've seen these last several weeks where we get some snow, that snow melts, we get a little bit more snow. And so rather than one big melt injection into the system. Instead, we're getting these pulses of melt as these snowpacks melt throughout the season. So I was interested in what this meant for the hydrology of the region. And the significance of this, it's significant in several different areas in terms of the ecology. Spring is a very critical time for many important freshwater fish species in Michigan and the Great Lakes. Many salmon and trout spawn during the springtime. And so any changes to stream temperatures or flow are going to impact those spawning rates of those fish. This is important for infrastructure because if we have flooding shift from the traditional spring when we have those big influx from melt to the winter months, that could have management implications. And of course, the Great Lakes is one of the largest freshwater reservoirs on the planet. And so any changes to one of the components of the hydrologic cycle in the Great Lakes is worth investigating. And then economically, this is also important, as I'll show towards the end of my presentation. I did a little bit of research into some aspects of snow tourism relating from these changes to snow. And so there are significant economic impacts that could result from some of these changes that we'll see. Now, specifically, the objectives of my dissertation were to first identify winters that were warmer or cooler relative to a longer term norm. And then once I have that warm or cool classification, I can then, through that lens, quantify the changes to snowmelt, both in terms of when snowmelt occurs, how much snowmelt is entering the system, and the frequency of when snow is melting. And then subsequently, what does that mean for the hydrology? What does that do to our surface water flows, the amount of flow, the timing, as well as the amount of shallow groundwater recharge that we're getting? So I approached this in 4 different chapters. The first chapter I call here laying the foundation, but really it's just establishing the methodology. And so I do this over a small temporal and spatial scale, and then develop my approach that I then apply in subsequent chapters, such as the second one, where I expand the temporal and spatial scales pretty significantly, looking at a much larger area over several decades of time. And that way I can much more confidently establish this link to climate. And then the third chapter, I call it filling in the gaps, the data gaps, because I'm interested in the entire hydrologic cycle. And groundwater data is not as available as surface water data. And so in order to really get a handle on what's happening to the groundwater system, you have to do that through simulation modeling. And then finally, as I mentioned, the last chapter of my dissertation tried to make things a little bit more tangible that we're seeing, looking at some economic effects of that within the state of Michigan. So for chapter 1, as I mentioned, I just looked at a small area. So just looking at the state of Michigan from 2003 to 2017. For this, I used a combination of observational and modeled data. So I relied on 240 Global Historical Climatology Network, or GHCN stations, for my temperature and snow depth. That's these green dots here in the middle panel. And then I utilized 123 USGS stream gauges for my surface water data, and those are the red dots in the far right. And then a lot of my snow data, the depth and the snow water equivalents, or SWE, how much water is contained in that snowpack. I used NOAA's SNODOS model, which puts out 1 kilometer grid scale daily time steps of snow depth and SWE and other different variables across the continental United States. And that's what dictated my temporal period, because that didn't become available until 2003. So I utilized 3 different spatial aggregations when I looked at this data. The first, and most of the figures that you'll see will use this panel A breakdown, where I broke up the state of Michigan into 3 different regions. So I've treated the UP as its own region, and then I split the lower peninsula in half, and I did this to capture the regional differences that we see in snow. So this figure is showing the annual snow in millimeters of SWE, snow water equivalents, across the region. And this is from that NOAA SNODOS data. And so you can see in the Upper Peninsula, we're getting very large quantities of water from snow, areas like the Keweenaw, where we're seeing close to half a meter of SWE in some years. And then in the northern Lower Peninsula, we get a little bit less snow, but still more snow than we see down here in the southern Lower Peninsula, where most of us are located now. In panel B, this is showing then HUC-8, or Hydrologic Unit Code drainage basins. So a lot of the snow analyses that I performed were utilizing these drainage basins. And I did this because the Huck drainage basins, they're contiguous. They completely cover the area without overlapping anything. And the Huck 8s provided a good size for this first pass at our analyses. And then finally, a lot of the surface water analyses that I performed, I utilized these drainage basins that we created using the National Elevations Dataset, DEM. And so that's these polygons here, and these are color coded by the state region that they fall into. And so this was just to focus in on the surface drainage while I was looking at that gauge data. So the first step in this process was classifying winters as warm or cool. And I did that through this multimetric analysis that I developed. So the first thing that I would do is I would take the daily temperature data from the GHCN stations, these green dots, and then I would first aggregate it across these Huck 8 watersheds, so that if there are multiple stations within one basin, then I would just average across those for one temperature for that Huck 8. And so I did that for 6 different metrics. I had 3 different seasonal breakdowns. I had the entire snow month, the month that we would expect to see snow in Michigan, so October to May, and then just the winter months, December, January, February, and just the spring months, March, April, May. And for each of those 3 seasons, I looked at the mean and the minimum temperature. So that gave me a total of 6 metrics that went into this multimetric analysis. So once I had those 6 temperature values for my Huck 8s, I calculated the metric score using this z-score formula, where I just had, in this case, say we had one of those metrics for a Huck 8 for 1 year, and then I subtracted the mean across all of the years. So in this case, 2003 to 2017, and then you divide by the standard deviation of that sample. And so what that tells you then is, for each of those temperature metrics, how much does it deviate from the overall norm, in this case from the 13-year norm. So I had then this z-score, this metric, and then I took the mean of those 6 z-scores, those 6 metrics, for each of those Huck 8s. So that each Huck 8 had a metric score for each year. And then finally, in order to classify individual years as warm or cool, I averaged those multimetric scores across all of the Hucks in the state for one overall statewide score. And so scores that were above 0.5 were deemed warm, and that were below minus 0.5 were deemed cool. And so that gave us 4 warm winters, 2004, 2010, 2012, and 2017. And then 5 cool winters, 2008, 2011, 2013, 14, and 15. And it's interesting to note here that some winters, like 2012 or 2014, they're pretty homogeneous. It's all blue or all red. All of those basins are showing those warmer or cooler temperatures relative to the norm. But then we have some years, like 2017, where you got a lot of blue in there. Now it's a light blue, so it's hovering around that 0 point, but then some of those basins are warm enough, or red enough in this case, to drag that overall statewide average up above that 0.5 threshold to classify it as warm. So then, using those warm and cool year classifications, the first thing I look at is the snow, of course. And so this figure on the right is showing us day of water year on the x-axis. So day 1 is October 1st. We have mean snow water equivalents in millimeters on the y-axis. And then each of the panels is one of our state regions. So the Upper Peninsula up top, Northern Lower Peninsula, and Southern Lower Peninsula. Now the solid blue line is the mean SWE on that day across the region for cool years. And then the solid red line is the same thing, but for warm years. And then the shading is just the spread of the data. So all of the data points within that day for that year type. And so a couple of things to note with this. The first is what we would expect to see is there's a latitudinal gradient, where as we move north, regardless of which year type we're in, we're seeing more snow. So you get more snow in the UP than you do in the Northern Lower Peninsula, and so on. But if we look at the differences between years, a couple of things stand out. The first is that throughout the winter, these warm winter SWE values are lower throughout the winter than they are in the cool winters. They have lower peaks than what we see in the cool winters, those peaks typically are occurring earlier than we see in the cool winters, and the snowpack is melting earlier in the warm winters compared to the cool by several weeks up to over a month in some cases. The other interesting thing to note about this is it seems to be more of a difference in the more northern regions than in the southern regions. So if we look at the difference between the cool winters and the warm winters in the UP, it's much larger than what we see down in the southern lower peninsula. And a lot of that, I believe, is just because the southern lower peninsula just inherently doesn't receive much snow regardless of what year type it is. And so those differences aren't as dramatic compared to the UP, which receives a significant amount of snow. And so those differences become a lot more apparent. Now, in terms of the melt that we're getting, these are some violin plots of melt events in both warm and cool winters for our regions. So the wider the plot is, the more data points fall at that particular range. And so up top, we have the total melt in millimeters. And again, we see that latitudinal gradient where it doesn't matter if you're in cool winters or in warm, as you move northward, we're getting more melt as you would expect. But we're getting more melt events in these warm winters regardless of the region. And so a melt event is just defined as consecutive days where that snowpack SWE is decreasing. And more of those melt events are going to completion. So when those subsequent days of decreasing SWE happen, they end with zero snow on the ground. So in these warmer winters, we're having less melt. Those snowpacks are melting more frequently and more often until there's no snow left on the ground. Now, what does this mean for our hydrology? So this figure here on the right is showing us the median basin yield in millimeters. So that's just the discharge of the stream divided by the basin's area. And so again, day of water year on the x-axis, we have a regional breakdown with the UP up top and the southern lower peninsula down below. Again, our blue line is our median across those cool winters and the red across warm winters. This gray shaded box is showing us those snow months, so that October to May period that I had defined. And we can see that in terms of our basin yield, especially in the UP, we have much lower flow in the spring, lower basin yield in those warmer winters compared to what we see in the cool winters, with that cool winter peak being much, much higher. And it's also much later. And we see this in the northern lower peninsula, although just like the snow, it's not quite as significant of a difference. And then in the southern lower peninsula, it's mainly a timing difference, but the amounts are very similar. Now, the timing of the center of discharge volume, or CDV, which is represented by these vertical lines, is also earlier in these warmer winters. And so what this CDV is if we just take this gray box, the snow season, and look at when has 50% of that period's basin yield occurred. And so we can see that in the UP, it's earlier by several weeks. In the northern lower peninsula, it's pretty close together, and then it starts to widen back out in the southern lower peninsula. But again, regardless of what region of the state that we're in, we're seeing earlier flows in these warm winters, more of a shift into the winter for these peak flows that we see from the snowmelt influence. And then for this first chapter, I tried to look into what was happening with shallow groundwater. And so I did that by estimating the net recharge using a simple water balance equation where I said the change in groundwater storage, or net recharge, is equal to our inputs, so rain plus melt, minus our outputs, which is just basin yield. Now, this is assuming that there's no evapotranspiration occurring, which for all of these months except maybe April is a pretty safe assumption. So over here on the right now, on the x-axis, we have months instead of day of water year. This number in parentheses, that's just the first day of water year for that month. Up top, we have monthly net recharge in millimeters. And so we can see, especially in our lower peninsula regions, throughout the winter, those winter months, January, February, we're seeing more of that net recharge in those warmer winters. And then as we progress into the spring months and those cool winters start to get that snowmelt influence, it starts to shift in our northern regions and we start getting more recharge. Now, these differences are a little bit more, a little bit easier to interpret when we look at this cumulatively. So down below, this is the same data as we see in the panels up top, but it's just plotted cumulatively. And so we can see in our southernmost region of the state that net recharge in warm winter starts out high. We get that really high increase in the winter compared to our cool winters. Then it remains high throughout the rest of those snow months. And as we move northward, again, we see that higher net recharge in those warm winters in the winter months. But by the time we get towards the end of the snow season, those differences between warm and cool winters start to become negligible. And then finally, when we get to the upper peninsula, it shifts. And so once that snow melt starts to kick in April in the UP, suddenly we have way more cumulative net recharge in those cool winters than we do in the warm. And again, just because we're getting so much more snow in those cool winters in the UP than in the warm. But again, all of that was a very short time period, a very small spatial scale. And so for my second chapter, I really wanted to establish some of these relationships that we're seeing at a much longer time scale over a much wider area. And so to do that, I looked at the majority of the eastern US. So these are now Huck 4s, so the same hydrologic unit code basins, just a couple of steps up. I looked at now from October of 1959, or the start of water year 1960, until May of 2019. And this relied entirely on observational data because most snow and climate models, they don't go back as far as I wanted to go. And so I wanted to just look at what the observational data was saying. And so I utilized 1,369 temperature stations and 1,725 snow stations from that GHCN weather stations. And so the locations of those are denoted in this top map. And then for my surface water data, I utilized 1,751 USGS stream gauges. And again, now that's depicted in that bottom panel. And I determined my domain extent by just looking at where snow was occurring. So the southern boundary of this domain, below this, if you go any further south, you're not going to see enough snow for it to be a significant contribution to the annual water budget. So we're getting down to less than 35 centimeters of snow a year. And so it's not enough snow to be very meaningful. To the west, this is bordered by, we're starting to get into the foothills of the Rockies. And so I wanted to avoid some of the orographic effects that we'd see from those elevation changes. And so that left us with this northern and eastern sections of the country. And so you can see the distribution of snow is pretty wide across this area. We see that influence of the lake effect phenomenon, where areas like the UP are getting large amounts of snowfall every year in parts of the northern lower peninsula. We see the same thing over on the east part of the Great Lakes in western New York and Pennsylvania. And then up into New England, we start getting some more influence from the North Atlantic and those nor'eastern storms that they get out there. So I applied the same multimetric analysis that I did in chapter 1 to these larger area and longer time frame. The only change that I made is, rather than classifying overall years as warm or cool, I let it remain basin specific, so that one basin might have a warm year while a different basin might not be classified that particular year as warm. I let it be specific to that basin's overall average or norm. So this figure is showing you each of those Huck 4 basins and the number of warm winters using that multimetric classification in that decade. And so we can see in the 60s and 70s, it's pretty light colored. Most of these basins are seeing 1 or 2 warm winters out of the 10. We get into the 80s and 90s, and we're starting to see a little bit more red. Now we're getting 2, 3, or 4 warm winters per year, until finally we get in the more recent decades, and now we're seeing some really dark reds, and especially in the 2010s over on the East Coast. Now we're getting up to 8 out of the 10 winters in that decade for some of these basins classified as warm compared to the 60-year norm. Now, not only are we having more of these warm winters, but these winters are becoming warmer as well. So now this is the same figure, but instead of the number of warm winters, we're looking at the mean metric score for that basin for that decade. So lots of blue in the 60s and 70s. You can see the mean, we're in the negatives, we're below, colder than that 60-year norm. We get into the 80s and 90s, we're starting to see a little more red, but it's pretty light shaded. We're hovering around that 0 point, that norm. And then again, once we get into these recent decades, now we're seeing more of those red colors, more of these warm winters. And so again, especially along that East Coast there, we're seeing much higher multimetric scores in the 2010s than in previous decades. And this increasing trend can be seen in a time series of this data. So this is season or water year on the x-axis. This is the metric score on the y-axis. So each of these points represents the mean multimetric score across all of the basins in the domain for that year. The shaded gray line just shows the standard deviation for that decade. We've got our 0.5 warm winter threshold here in red, and then our minus 0.5 cool winter threshold in blue. And so this dashed line is the overall trend of these metric scores. And so as we just saw from the previous figures, that's increasing. The green line is the decadal average or decadal mean, and that's also increasing. We see what we just saw in some of those previous figures where the 60s and 70s, it's in the negatives and the cooler scores. 80s and 90s were around that midpoint. And then as we get into the recent decades now, we're moving more into those warmer scores. But what's really interesting about this figure to me is not only are we seeing an increase in these multimetric scores through time, but we're also seeing an increase in the spread of the data. So the standard deviation in the 2010s is larger than any of the other decades. And we've got our warmest year, 2012, and our coolest year, 2014, both within that same most recent decade. And you can see that in this GIF that I made. This is just the multimetric score for each basin for each year. And so you see as we go through time, we're going to start seeing more of those red colors. Those reds are going to become darker, but we're also going to see some really dark blue colors. And those years that I pointed out, 2012 and 2014, are really going to stand out compared to some of these previous years that this goes through. Really red and then really blue. So we're seeing that wide range of distribution. Now, what does this mean for the snow? So this figure here on the right is showing the median bare ground days for each of these HUC4s, with this blue line denoting the 67% line. So if you go south from this line, then 67% or more of the days in winter have bare ground. And if you go north of it, then it's less than that. And so in the 60s, that line, it cuts through South Dakota, kind of following along the southern boundary of the Great Lakes, barely getting into Michigan. And then as we get into the 2010s, that line shifted northward. Now it's all the way up into these more northern states. We're getting across basically right through the middle of the lower peninsula, getting up into New York and into New England. So with these northern regions starting to see more of their winter without snow on the ground. This can be seen within the overall trend of these bare ground days. So this figure is showing the bare ground days per season slope across the entire 60-year period. And you can see there's only a couple of these basins that aren't red, that aren't showing an increasing trend through time of more bare ground days. And the shape of the snowpack also reflects this. So now we've moved up a scale again. So now we're into HUC2s. So it's the same data. I'm just looking at it through a larger lens. And so again, blue line is the cool winter median and red line is the warm winter median of depth. Now this is depth, not SWE, because I'm going off the observational data, and SWE is typically not very common in observational snow data. But we can see that in these cool winters, especially in the more northern regions, that snowpack is much, much thicker in these cooler winters. We've got a much higher peak. That peak is occurring much later in the season. And then that snowpack is melting much early or much later in these cool winters compared to warm. Again, several weeks to over a month in some of these basins. And our basin yield also reflects some of the trends that we saw in chapter 1. So now we've got, again, day of water year on the x-axis. We've got that median basin yield in centimeters on the y-axis. Each of our panels is that HUC2 region. And so again, we can see that we've got higher peak flows in the cool winters compared to the warm. Those peak flows are occurring earlier in the winter and warm winters compared to cool. And that CDV time is also shifting earlier in these warm winters and all but the southernmost basins that aren't receiving very much snow. But you'll notice that that second chapter, the one thing that I didn't talk about was the groundwater, because again, for that long of a time period going back to the 60s, groundwater observational data is pretty scarce. And so in order to look at what's going on with the groundwater system, I had to turn to simulation modeling to try and figure out what's going on there. And so I did that using the Landscape Hydrology Model, or LHM, that was developed by Dr. Anthony Kendall in the Hydrogeology Lab at Michigan State University. And so LHM is a process-based, fully discretized model that incorporates a variety of landscape and climate inputs. It's got climate data from NLDOS. It's got a variety of land use and geology inputs that go into it. And so it takes all of that data and then it looks at how much of that rain or snow infiltrates the subsurface and recharges the groundwater, how much of it runs off into surface waters, how much is lost to ET, and then it can be coupled to mod flow so that you can feed to mod flow the recharge that LHM says is occurring and see what's happening to the groundwater flows. And so for this, because I was limited in my processing power capabilities for the model, we shrunk the scale back down to Michigan and just looked at the last 20 years. And we did this at 1 kilometer grid scale. And I, again, used 3 different spatial aggregates for this. So the first is what we came to call the sliced model grid. So if we had the entire 1 kilometer by 1 kilometer grid across the state, that's a lot of cells to run. And so when we ran the model with the entire grid, it could take a couple of days for the entire 20-year period to run. But these black dots represent the GHCN stations that have snow data that we could use for observational data. And so we could look at just these cells where those snow stations are located and just generate the outputs for those cells. And it greatly increased our processing speed. It went from a couple of days down to a few hours, an afternoon. And so we were much more rapidly able to compare the model to what the observational data is saying, modify the simulation, run it again, and keep going through that process iteratively until we had it where we wanted it. The other spatial scale I utilize is the HUC-10 basin aggregates, which are these shapes that are outlined in black. Because I was using 1 kilometer grid scale, I was able to look at things at a little bit finer resolution and use the smaller basins than the HUC-8s that I was originally using. And then finally, this regional breakdown across the state that you're going to see a lot in the visualizations of the model outputs. Instead of the 3 regions that I used in chapter 1, now I tried to capture a little bit more of that influence from the lake effect. So I split the Upper Peninsula in half, and then instead of splitting the Lower Peninsula in half, I put it into quadrants, because even if you're in the southern Lower Peninsula, you're going to have more snow on the west side of the state than on the east because of that lake effect. And I was really trying to capture that. So then looking at LHM's snow model, so this is now month on the x-axis, not day of water year. We have mean snow water equivalents again on centimeters on the y-axis. Again, blue is cool years, red is warm, and then we have a regional breakdown with our 2 Upper Peninsula regions up top, and then our northern Lower Peninsula regions in the middle, and then finally our southern Lower Peninsula down below. And so similar to chapter 1, we're seeing that snowpack in these cooler winters is peaking much higher. That peak is occurring later. And then these snowpacks are melting earlier in these warm months. So very similar to what we saw looking at the Michigan data in chapter 1. Now looking at the recharge, some interesting things come out. And again, it's interesting also that it's very similar to what I found with just that simple water balance equation I applied to the data in the first chapter, where in our winter months, in our January, February, we're seeing more of that recharge in the warm years compared to cool. But then in March, April, when that snow melt starts to kick in the cool winters, that starts to switch and we're seeing more recharge as that snowpack melts. But again, it's a little bit more useful, I think, to look at this cumulatively. So this is the exact same data, but just plotted up cumulatively through time. And so we can see in all of our Lower Peninsula regions that those winter months where the recharge is higher in warm years, that really sets that difference, and then it continues throughout the rest of the water year, so that by the end of the water year, we end up with higher overall cumulative recharge in the warm winters compared to cool. However, in the Upper Peninsula, we see this shift in the trend, where in the winter months, it's actually very similar between warm and cool winters. But then once we get that snowmelt occurring in April in the UP, that recharge shoots up, and by the end of the water year, we end up having more overall cumulative recharge in the UP in cool winters compared to warm. Again, this is likely just due to how much more snow they're getting up there in the cool winters. So as I mentioned, the last chapter of my dissertation was really looking at some economic effects of this. So part of my PhD was involved with the Environmental Science and Public Policy program at MSU. And so part of that program, one of the requirements was incorporating a policy aspect into my dissertation research. And so when I started to think about what would make this data meaningful to policymakers, well, what's going to make policymakers pay more attention than their money, than the budget? And so I wanted to look at what these changes to snow mean for the ski industry in Michigan. And so some context for that, the reason I chose the ski industry is that Michigan has the most ski slopes of any state in the Midwest at around 40 ski areas, give or take, depending on the year. And in the 2004 to 2005 winter, Michigan had the second highest number of ski slopes in the entire country, behind only California. In 2009-2010 winter, skiing and snowboarding added over $600 million to the state's economy, with almost 11,000 jobs associated with the ski industry. And outdoor recreation and tourism is the third largest industry in Michigan, behind only auto manufacturing and agriculture, with skiing being the most popular winter recreation activity. So it's a very large part of our state's economy. And it's an industry that's already facing challenges from these warmer winter temperatures. Currently, 76% of Great Lakes ski slopes could be considered economically viable. Their net income is enough to sustain them for the foreseeable future. But under a high climate emission scenario, that decreases to just 7 or 8% by the end of the century. Again, under a high emission scenario, the holiday ski period, so about that 2 weeks around Christmas and New Year's, that's when a lot of these ski slopes get their annual income. A lot of people go to the slopes on those days. And so that holidays period is reduced by 66% under a high emission scenario, with a greater than 50% decrease in snow depths during the 2-week window. And by the 2080s, days with sufficient depths for snow or for winter recreation could be up to a month shorter, with less than a month per year with suitable temperatures for snowmaking, because most slopes already supplement their snow depths with artificial snow, but you have to have the right temperature and humidity in order to create that artificial snow. And so not only will there be less snow, but the capabilities of making more snow is also reduced. And then finally, under a high emission scenario by the end of the century again, snowmaking requirements will increase by 516%. That we need that much more artificial snow in order to keep the slopes open, with the state's skiable terrain reduced by twice as much compared to a low emission scenario. So it's already seen some of these challenges. Now, for my analysis of this, I looked at the 21 Huckate basins across the state that contain ski slopes. So these black dots are the different ski areas across the state. These Huckates are just showing the average annual depth in centimeters of snow. And I looked at this from 2003 to 2020. Again, I started utilizing that SNODOS data because it had that spatial coverage, that gridded coverage, and that only became available in 2003. And then I looked at the snow depths in warm and cool winters for these ski basins. And I did that utilizing, again, that GHCN temperature data. And I looked at how many snowmaking days we could have. Again, you have to have suitable temperatures to make artificial snow. I looked at visitor totals from the National Ski Areas Association. And then I was also provided some additional data by Pete Bigford, the CEO of Shaney Creek Resorts, which is this red dot up here by Traverse Bay. And he provided me with some data on their water usage and the time that they spent applying this artificial snow to their slopes from 2013 to 2021. So looking at the snow in those ski areas, again, day of water year on the x-axis, depth in centimeters on the y-axis. This dashed line represents 30 centimeters. That's, according to the literature, the minimum depth required for skiing. So below this line, you're going to have to supplement the snow on your slopes with that artificial snow. These vertical lines represent that 2-week holiday period that's critical to a lot of these ski slopes budgets. And of course, again, we've got blue lines for cool winters, red lines for warm. The solid line is for the Huckate Basin that contains Shaney Creek resorts. And then the dashed line is for all of the basins that have ski slopes in the state. And so as we've already seen with the previous results, we've got lower snow amounts in those warm winters compared to cool, lower peak amounts, that snowpack is melting much earlier. But what's interesting in this figure is in these warmer winters, there's only a couple of days, maybe a couple of weeks, where that's getting above that 30 centimeter threshold for when you have enough natural snow to ski on. Whereas in these cool winters, we've got several months where it's getting above that 30 centimeter depth. Now, these are those violin plots again. So again, the wider the figure, the more data points at that particular y-axis value. And so in this top panel, we've got days with depth greater than or equal to that 30 centimeter threshold. And so we can see in these warm winters, most of those basins are getting close to that 0 point. They don't have very many days where the natural snow depths are high enough to ski. Whereas in these cool winters, you got a pretty large distribution where you're getting some of those basins several months or more of depth sufficient for skiing. Now, if we look at snowmaking capabilities, according to the literature, you need less than 2 degrees Celsius in order to make artificial snow. Now, there's a lot more of an influence from humidity, but humidity data is not nearly as widely available as temperature. So I stuck with temperature for this. But so again, we can see in these warmer winters, we've got significantly less days where the temperatures are suitable for making snow. So not only are we having less natural snow that's suitable for skiing, but our capacity to make artificial snow to supplement that is also decreased. And then getting into the Shanty Creek resorts data that I got from Pete Bigford. So over here on the right, we again have day of water year on the x-axis. We have that 2-week holiday window denoted by the vertical lines. And then rather than aggregating across the warm and cool winters, because I only had data back to 2013, and there's only a handful of those years for each classification, I just decided to plot those years individually and then color code them by their year type. So then up top here, we have the cumulative water use for making artificial snow in cubic meters. And then down below, it's the cumulative hours spent making artificial snow. And what's interesting here is this is cumulative. And so in our cool winters, we start making artificial snow earlier in the year. But by the time we get close to that holiday window, those warm years start to ramp up as they expect more visitors. And then what's really interesting about this is that by the end of the season, we actually end up using more water and spending more hours making artificial snow in those cool winters. But I think that this is mainly due to the amount of visitors that they're getting in these cooler winters. So looking at across the Midwest, the amount of annual visitors that are attending these ski slopes, there's about 7.1 million visitors in these cool winters on average, which is 300,000 more than we're seeing in warm winters. So what I think is going on there is because they're seeing more people are looking outside their house and seeing their snow outside and think to themselves, well, let's go skiing this weekend. And so they're having more visitors that they want to keep happy. And so they're increasing those depths, even though there's already sufficient natural snow depths for skiing present. However, even though we're seeing more usage of water and more hours spent in these cool winters, they stop applying that artificial snow much earlier in the season. Once they get to late January, early February, they decide they've got sufficient snow depths to last them through the rest of the winter. Whereas in these warmer winters, because those warmer temperatures are decreasing that natural snow, we don't have as much of that snow reaching the 30 centimeter depths. They have to keep applying that artificial snow through the remainder of the ski season. However, again, this only goes back to 2013. This is just one ski resort. So that's just one thing to keep in mind, is that it's a limited data set. And so the interpretations made from this are not the strongest. So just to wrap things up in conclusion, we're seeing warm winters are getting warmer and more frequent in Michigan and the eastern US. These warmer winter temperatures are resulting in decreased snowpack depths and snow water equivalents, decreased peak depth in SWE, earlier melting of that snowpack, more frequent melting throughout the winter snow season, and an increase in the amount of bare ground days per season. Hydrologically, this is leading to higher winter stream flows, earlier and lower peak stream flows in the spring, an earlier center of discharge volume time, and an increased shallow groundwater recharge, especially in the winter months and in the southern basins of the regions that I looked at. This is leading to less ski slope visitors in those warmer winters, less days with suitable snow depths for skiing or temperatures suitable for making snow. And at this point, as I said, with the data that I had, the effects then on resource usage for snowmaking are unclear, but it's a safe assumption, I think, that as temperatures continue to increase, there will be more pressure to create that artificial snow, despite the fact that conditions won't be ideal for it. So just to acknowledge some of the funding sources for my PhD studies, I received support from the MSU Hydrogeology Lab and Department of Earth and Environmental Sciences, as well as the Environmental Science and Public Policy Program at Michigan State. And then I was supported through several grants from USDA, NEFA, NASA, and NOAA. And then, of course, this was the end of my dissertation defense, so lots of personal support from friends and family and colleagues as well. So thank you, and I'll take any questions.
Go ahead and speak up if anybody's got any questions.
I have a question. Have you shared this information with ski associations in Michigan? Just curious their response.
No, I have not. The last chapter has not been published yet, and so it's kind of one of those things that got put on the back burner as you know, we have every intention of getting that data out there, and we especially want to get it back to Pete Bigford, since he supplied a lot of that data from Shaney Creek. But no, I haven't shared this with any sort of ski associations.
Yeah, I know that there's many of those organizations. Outside Magazine, you know, Save Our Winters is a pretty popular topic right now. As a skier and a snowboarder, I was at Cabernet last Friday. I am concerned. So thanks for your talk.
Yeah, thank you.
Chance, do we have your permission to share this recording with other members of the society?
Yes, that should be fine.
How about sharing your PowerPoint slides?
Tentatively, yes. I say that because in order to share the slides, even though this was for my dissertation, being with USGS now, I would likely have to go through our internal review process to distribute those. So that might be something we have to follow up on.
Sure, I understand. Well, thank you, Chance. That was a wonderful talk, and I'm sure we all enjoyed it. And if there's nothing else from anyone, then we'll go ahead and end the meeting. So anybody have anything else to say?
Thank you, everybody.
Thanks, Milt.